Hello everyone. Today we are going to discuss about magnetic circuits. The magnetic circuits fundamentals. Here in this class we are going to discuss about what are magnetic circuit, what is Lenz law, Fleming left hand and right hand rules, the terms associated with magnetic circuit, and finally we'll discuss hysteresis loop. Now, what is a magnetic circuit? Magnetic circuit in which response versus excitation characteristics depends upon the development of magnetic flux are known as magnetic circuit. Similarly, in an electrical circuit, when we are going to apply some potential source through some source, then current will flow in the circuit. In a magnetic circuit, when we are developing some magnetism, always there is a flux. Now, if suppose the magnetism can be considered as permanent magnet and temporary magnet. In case of electrical system, the magnet is temporary magnet. As long as there is a electrical supply, there will be a current in the circuit, and due to this current, the flux will develop in this coil, and this resultant flux will be categorized as north pole in this space and south pole, since magnetic lines of force will coming out from the north pole and entering into the south pole. Within this core of the or this material, the magnetic lines of force moves from from south to north pole. Now, the best example of this magnetic circuit is electrical transformer. This is the symbolical representation of transformer. In this case, we are having two coils. One coil is placed over this limb of this transformer core, another coil is placed in the second limb of the transformer core. When we are going to apply some potential over here, then EMF will develop in the secondary as well, because of the flux linking in primary and secondary is same, and this EMF development is because of the electromagnetism within the circuit. Now, what are the source for electromagnetism? Is known as magnetomotive force. Similarly, in electrical circuit, we are having EMF. EMF means electromotive force, whereas in magnetic circuit, which causes the development of flux, is known as magnetomotive force. The ability of electromagnetic field to develop flux is known as electromotive force. Now, the unit of this electromotive force is ampere turns. Ampere turns here means current into the number of turns, that is Ni. Now, flux. As the case of electrical circuit, there is a current, whereas in case of magnetic circuit, there is a flux. Flux is the total number of magnetic lines of force in a magnetic field is known as flux. It depends upon flow of current and the number of turns. Its unit is Weber. Now, if there is some motive force or which causes some flux, always there will be opposition to the development of this flux. In electrical circuit, the opposition to the flow of current is resistance. Similarly, in magnetic circuit, the opposition to the development of flux is reluctance. Reluctance is represented by S. The property of material by which it opposes the development of flux is known as reluctance. The unit of reluctance is ampere turn per Weber. If in any magnetic circuit here means the coil, this coil is energized with supply AC or DC, then there will be some EMF develop in this circuit, and is the EMF flux develop in this due to this coil, it depends upon current and the number of turns. These are the number of turns. Now, if n is the number of turns in this circuit, let it is n. The current flowing in the circuit is I. The flux developed in the magnetic circuit is flux is directly proportional to I, and it is directly proportional to n. Considering this flux, these two components n and I, flux can be directly proportional to n into I. Now, to remove this proportionality factor, it can be written as Ni upon S, where S is nothing but the reluctance, which opposes the development of flux. By the property of the material, S is equal to L upon mu A, where L is the length of the magnetic path through which this flux passes, mu is the permeability, and A is the cross-sectional area of the magnetic path. In case of electrical circuit, we know R is equal to rho L over A. where A is the cross-sectional area, L is the length, and rho is the resistivity. In this case, if S is the reluctance, L is the length, A is the cross-sectional area, and mu is the permeability. Now, putting the value of S in this equation for flux, then it will be Ni upon L mu A. Further simplifying this equation, as we know, flux density B is equal to phi upon A. This phi and upon A is replaced by B. The rest of the component is mu and L, that is BL upon mu. By the definition, we know H is equal to B upon mu, and hence Ni will be equals to HL. If Ni is equal to HL, then we can easily find out the value of H will be equals to Ni upon L. And further, we can rearrange this component to find if other three values are known to us, the fourth value can be calculated. Now, what is Lenz law? The importance of Lenz law in magnetic circuit is very important. Magnetic circuit point of view, Lenz law is a very important concept. According to Lenz law, the EMF developed across a conductor always opposes the cause producing it. What does it mean? Suppose we are having a magnet with north pole and south pole. One conductor is placed within the periphery of this magnetic field, and neither this field is changing nor this conductor is changing. There will be no EMF in this conductor. Now, suppose we are moving this conductor in the direction of north pole, and hence it is earlier it was having some number of magnetic lines of force cutting with it, but now it will cut more magnetic lines of force, and hence it will develop its own magnetic field which will oppose the cause. The cause is here is these magnetic lines of force, and the magnetic field developed by this conductor will be opposite to this, and hence it is only possible when this current is conductor is entering, whereas the current in this point is leaving. And when current is leaving over here, by applying this the concept of Lenz law, the magnetic lines of force are entering, more magnetic lines of force are crossing this conductor, whereas this conductor will allow to oppose it. At this point, this conductor is magnetic lines of force are in this direction, whereas in this part the magnetic lines of force is opposite, and hence there will be some opposition to the development of this flux. Similarly, when we move this conductor away from this magnetic field, it means the magnetic lines of force going to be reduced. Whereas, according to Lenz law, it always opposes the cause producing, and hence it will try to increase these values. And increment here means if magnetic lines of force are passing in this direction, the magnetic field developed by this conductor will also be in the same direction, and hence both will be additive, and hence it is trying to be increase the magnetic lines of force. Now, the another important concept is Fleming right hand rule. The Fleming right hand rule is nothing but when we are stretching out the right hand three fingers, the first finger, second finger, and thumb of the right hand are stretched out mutually perpendicular to each other. The first finger indicates the direction of magnetic field, and the thumb indicates the direction of force on a conductor placed in a magnetic field. Then the second finger, this is the second finger, this is the first finger, this is the thumb. Now, if first finger represents the direction of magnetic field and the thumb represents the direction of motion or force, then the second finger represents the direction of EMF or current in a conductor when it is placed in a magnetic field. Though this particular rule is applicable for the development of EMF, and hence it is used in the generator. Therefore, it is also termed as generator effect. The next is Fleming left hand rule. This is also important concept in magnetic circuit. When now here we are stretching out three fingers of the left hand, thumb, first finger, and second finger. If first finger represents the magnetic field, it was representing magnetic field in the right hand rule as well. Then the second finger represents the direction of current or EMF in the circuit. Then force or the motion of the conductor can be represented with the help of thumb. It is used to find the direction of motion or force developed in the motor, and therefore it is also termed as motor effect. Now, the another rule is thumb rule. The thumb rule is when we are knowing the direction of the current in a conductor, then we can find out what is the direction of magnetic field in surrounding the conductor. We know in electrical system, when conductor is passing through a conductor, it always develop a magnetic field. The direction of that magnetic field can be find out with the help of thumb rule. And here, if this is the direction of current, then the finger represents the direction of magnetic field. This is the circular path is nothing but the direction of magnetic field. Suppose the direction of current was downward. If it is downward in this case, then the magnetic lines of force will be opposite. This is the significance of the thumb rule. Now, the terms associated in a magnetic circuit. The magnetic circuit, the important concept is BH curve. The BH curve here means in a magnetic circuit, when electric field intensity is applied, it starts developing a magnetism. The development of this magnetism goes on increasing as we increase the current in the circuit, because H depends upon Ni is equal to HL, and here H is equal to divided by L, and it will be NIL. If the conductor number of turns is constant, the length of the conductor we have taken is constant, we can vary current. It means for the variation of this magnetic field intensity, we are varying the current. With the variation in this current, the flux density, that is phi upon A, and A is the cross sectional area which is constant, then flux will going to be changed. Then with the increase in the current, the flux in the circuit in a magnetic circuit will going to be increased, but a stage will come when with further increase in current doesn't allow any change in the flux, and that point is known as saturation point. This curve drawn between the field intensity and flux density is known as BH curve. Now, different material are having different BH curve. For example, alloy steel is having this curve when it is going to be saturated at this point. The silicon steel is going to be saturated at this point, whereas cast iron is going to be saturated at this point. Different material having a different magnetic property. Now, hysteresis loop. In earlier slide, we discussed about when we are increasing the field intensity, the flux density also increases. At the stage, it will going to be saturated. Saturation. At this saturation, if we start decreasing the field intensity, it doesn't follow the same path. Now it is following the different path here. And now at this point, field intensity becomes zero, whereas the magnetism is not zero. This is known as residual magnetism or retentivity. The property is known as retentivity. Why? Because once a magnetic material is made a magnet, it stores some magnetism within it. Even when we are applying the reverse magnetism, so that this magnetism stored within this magnetic material becomes zero, that extra force is required, which is known as corrosive force, and this property is known as corrosivity. Now, if we further increases this magnetic field in negative direction, with the increase, then again there will be a saturation at this point. Saturation at this point, and again we are going to reduce from negative to the positive direction, and it will be zero at this point. Now, at this point there will be a magnetism, but it will be opposite to this one. These two magnetism are different. What does it mean? In this case, if it was north, it was south. In second case, it will be north and it will be south. This magnetism will be zero when this much extra force is developed in the magnetic circuit. Then again we are following this path and completing this point up to this point. Then this curve, the whole curve is known as hysteresis loop. This path traversed from this point, A point, B point, C point, D, E, F, and back to A. A, B, C, D, E, F, and back to A is known as hysteresis loop. And different material has different loop, and depending upon this loop, this loop is a thick loop or this loop is a thin loop. The magnetic material is classified. The material which has thick loop is hard magnetic material. Hard magnetic material, the material which has thin loop, is a soft magnetic material. Hard and soft here means a magnet which is having thick hysteresis loop. Once it is made magnet, it store more magnetism even after removing the cause. Whereas in this case, it can easily made a magnet and easily can be removed the magnetism, and hence this is best suitable for electromagnet. Whereas this is best suitable for permanent magnet. Now, considering these two concepts, the transformer core is designed because transformer core is designed for electricity, and hence we do require thin magnetic material. Now, why? What happen when this magnetism is changing? Because we are having in AC supply, we are having a positive and negative. This is positive and this is negative. During positive cycle, the magnetism, all these magnetic dipoles will get aligned in one direction. Suppose this is north and this is south. In during the negative cycle, these magnetic dipoles will get reversed. And in this case, if they are aligned in this direction, though initially they are random in behavior, whereas when subjected to any electricity, they start aligning in one direction. Then if the supply gets changed, they will align in another direction, and this process of changing from this direction to this direction and this direction to this direction keep processed as long as supply is there. This is with the change in field intensity, the magnetic dipole changes their orientation with the direction of magnetism within it and produces heat. This is known as loss. Because this heat in transformer core is nothing but supplied from the input, and input is electricity. It means the power in the transformer or in any magnetic material due to the magnetism of reversal, the loss, power loss due to reversal of magnetism, is known as hysteresis loss. The hysteresis loss in core transformer core is derived empirically, and in a magnetic core, not only a transformer core, empirically, where n is the constant, hysteresis constant, bx is the peak flux density, 1.6 is the constant, f is the supply frequency, v is the applied voltage. Considering all these parameters, when we have tested this magnetic material differently at different time, different instant, with different magnitude of voltage, with different flux density, we obtain a relationship, and that relationship is known as empirical relationship, and which is given by pH is equal to neta B max power 1.6 F V watt, and this is the constant loss. When any magnetic material is subject to be an electromagnet, always there is a hysteresis loss, particularly when supply is AC.